Okay, welcome everyone. My name is Dable, or Deb, it's a very tab. I'm the president of the San Diego chapter of TiE. I want to thank our special guest tonight, Dr. Kingsmore and Ms. Wendy Benson. Thank you for coming. We look forward to your talk. I also want to thank Wendy Martins and Humphrey Choi. Is he here? Might be outside. Anyway, thank you to Wendy Martins for letting us once again use their beautiful space. So the mission of TiE is to foster entrepreneurship. And we do that. We've identified 5 pillars that are our guideposts in how we foster entrepreneurship. And I'm going to talk about 3 of those pillars tonight. The first is funding. Now last month, for those of you who attended our event last month, you heard from members of our sister chapter in Orange County about the South Coast Angel Investment Fund. And you might have heard how in just a matter of weeks, we raised over $1 million for the fund. And the goal of the fund, among others, is to invest in local startups in Southern California, Orange County, San Diego, to grow jobs. And so, as narrations here, our students here, there are other members who are involved and can provide you details. Let's see, or said leave. So anyway, if you're interested in the South Coast Angel Fund, please talk to any of us. You do have to be a charter member to invest, and I'll tell you more. We can tell you more about that later. Another one of our pillars is education. So we educate in different ways. One of the ways is these monthly events, like the one you're at right now. So when my first monthly meeting as president in January, I told the audience that our mission, our chapter here in San Diego, our goal is to get people outside of their silos. And I'm proud of the breadth and depth of the talks we've had this year. So I want to spend, because this is our last regular monthly meeting for this year, I'm going to spend a couple minutes talking about some of the events we've had this year. So those of you who are new, I talked to several people today who this is their first time to give them a flavor of vast areas they can learn about by becoming a TiE member. So in January, we talked about cell therapies, opportunities and challenges in cell therapies, and we had Dr. Paul Lycan, the president and CEO of Biochemistry, talk about that, as well as Dr. Srihari Sampath of Novartis. In February, we had a very different event. We had a Shark Tank-like event, which Steve is over here, Steve Morley. We hosted that along with the Brink Innovation Center. And I'll tell you, my son, he usually comes to these meetings, he's 10. And he was asking about that, when is Shark Tank again? And be sure to tell everyone that case that was invented, that we talked about in February was invented, it was all the TiE San Diego. I don't know if it was really all TiE San Diego, but it was certainly a fun event. In March, we learned about AI and machine learning from MapR. And then in April, we had Dr. Scott Struthers talk about the story of Crinetics, a San Diego company that he literally started in his garage and is now listed on NASDAQ. We went over to Dubai in May, learned about Dubai Internet City and what they're doing and what we can do in San Diego to grow businesses. We had a social in June, and then in July, we went all the way over to Drink Tech, and we learned from brewers and distillers across the county about opportunities and challenges in their businesses. And, of course, they brought samples, so that was fun. In August, we took a step back to reflect, and we had some of our members talk about lessons learned and reflect on lessons they have learned in biotech, wealth management, and real estate. And of course, last month we had another interactive event with neuroscience behind the retraining brain pathways, and that was a lot of fun. And we had quite a range of audience there. And then, of course, tonight we're going to be talking about unlocking the potential of pediatric medicine. So that I challenge you to find another organization in San Diego that gives you that sort of breadth. On the other piece in the education front is TiE, the TiE Young Entrepreneur Program. I think Devon was going to mention a couple of words about TiE. Most of you know what it is. I'm going to ask him to just give us an update.
Thank you, Devon. So, how many of you know what TiE stands for? Few, not everybody. So, it stands for the TiE Young Entrepreneurs. So, it's a program where we teach high school kids kids, all about entrepreneurship. And the most exciting thing that kids get to do is to prepare their idea just as if they were about to launch a venture. And then they go to compete with each other at a local level. And the local teams then go on to compete. The winning team will go on to compete at the global competition, which usually occurs somewhere in the US. This last one, for the 2018-19 cohort, the competition occurred at MIT in Boston, in Cambridge. And we just had Sandeep, who's heading up the whole program and has asked me to take on all the ambitious goals and accomplish them. And so the goals we have for this 2019-2020 cohort, which starts in January, to have 100 kids, 25 mentors, and probably 3 or 4 faculty members. And he's also working on setting up a foundation. So here's where we could use your help. We need to recruit 100 kids. The program starts in January, so we don't have much time. So if you know how to reach to certain schools in your residential area, parent-teacher association, etc., we would love to hear from you so we can help you make some announcements there. Secondly, we're looking to recruit board members. So board members have to be somebody who's in philanthropic community, well-known, can help us raise some funds and grants and scholarships that we're going to give out to the kids. And lastly, we need mentors who are successful entrepreneurs who've gone through the process, raised the money, launched successful startups, perhaps exited, who can come and teach these kids how to launch their own venture. The kids are so excited. Sandeep had organized a nice, quote-unquote, chaotic meeting this last Saturday, where he threw all kinds of things together, and then you could just see the magic happen. The kids, we had 3 or 4 prospective kids who were going to come in and enroll in the program. They didn't know much about it. And we had 4 kids from the winning team, and we videotaped it. We'll show it to you in the future, but it is amazing to hear their feedback firsthand, what they loved about the program, how they loved going to MIT and compete. And the kids that were thinking about enrolling in the program were just so blown away that I asked them, oh, would you like to join the program? Why would you like to join the program? And some of the comments they made are just absolutely fantastic. So we'll share that with you in the future, but in the meantime, we'd love to get your help. I'll be standing around in the back still eating food, so come and find me, and thank you.
That's at TiESanDiego.com. Along those lines, I want to recognize Dr. Rob Fuller, who's in the audience today, visiting from Utah. So Dr. Rob Fuller is one of our charter members. He's had a broad, interesting career, worked all sorts of different places. I'm just going to touch upon a couple of them, or 3 of them. SAIC, the State Department, UCSD. And he's currently actually a growth counselor at Optus. For 9 years at UCSD, Dr. Fuller was a lecturer to undergraduate and graduate students on courses in entrepreneurship. And 7 of those 9 years, he was gracious enough to spend his Saturdays teaching our TiE kids. So I'd like you to come up here, Dr. Rob Fuller, to, we have Marion and I, we have, pick up a nice gift for you. And while she's walking up here, so as I said, 7 of those 9 years, you taught our kids on Saturday mornings. One of those years, in 2016, you went to the global competition and swept the competition and won. When we say global, we're truly meaning an international competition. And that was the winning team in 2016. Last year's team also won a couple of awards at the competition. And so we're just so grateful for all that you have done for the TiE kids and the legacy you've created in them. And do you want to say a couple of words?
Thank you. as the outgoing director of the TiE program, I guess you could say, it has been a fantastic program. We've run a number of students through the program. We have something like somewhere around 100 alumni now. Many of them have gotten into very prestigious schools, many in the Ivy League, and they use TiE as one of their resume builders. TiE originally started out as a business planning competition, sort of a traditional business planning competition like you would see almost anywhere. We have several here in town, but it evolved into a business model competition. So the idea is not so much at the global level to have students be prepared to start a business, but rather to go through all of the experiments about coming up with an idea and then figuring out who would be their target market and what is the value proposition that they could develop around that. So students have taken a very different view. Some of them have done very casual kinds of programs for other high school students. We had one group, the group that took the global competition, they developed a chewable candy that increased focus. And they called it Focus 4, because it would increase focus for 4 hours. And then there were 4 of them. So a little play on words. We've had other students who developed medical devices. Some of the competition at the global level, people have been, students have built robots, students have built real medical devices that are being certified. Some have created businesses that went on, they actually started the business. Others, it was just an academic experience. So TiE has been a very interesting program, and I would encourage everyone in this room to go talk to Sandy, go talk to Diwali about participating in the program, because it is such a growth opportunity, not only for the kids, but for the adults who participate, to see and to guide and to mentor these students that are growing. I'm sad that I'm leaving, but I'm getting ready to retire from UCSD this year. My wife has bought a business up in St. George, Utah, and so it's kind of nice to be married again. So I go up and I spend time with her, and as soon as I retire, that's where I'll be. That's why I'm leaving the TiE program. But it's been a great honor, it's been a privilege, and it's been a whole lot of fun. So I would encourage you all to participate.
More research on your favorite kind of wine and vineyard, and hopefully it'll meet your approval.
Very nice. Thank you very much. Thanks, Rick.
Rob, we're not letting you go, you know that.
You think?
So and then on the final pillar we'll talk about is the networking pillar. Of course, we have the monthly events, and we have social events. Our next monthly event is actually in December, and it's going to be at the Cutwater Distillery. It's our holiday party, and we'll have tours of the distillery. The other networking way to network in TiE, which I haven't talked about this year, is the charter membership. And people have asked me often, what is the charter membership? Well, charter membership is a different level of membership. It's $12.50 a year. It's an opportunity to give back to TiE, including to TiE, and also an opportunity to have fun events with people in this room and across our community. So we have several events coming up for charter members. On November 3rd, we have our Diwali Gathering with South, since we have physicians in the audience especially. It's the South Asian Physicians Organization. We're going to have a Diwali party with as many fireworks as legally allowed, which is not a lot, but that'll be fun on November 3rd. And then on November 10th, we have a secret table dinner at a farm in Encinitas, where those who are willing will be blindfolded and get to taste test different things. And after the blindfolds come off, there's going to be entertainment by the San Diego Circus Center. We also are planning an event later in a few weeks with the Asian behind-the-scenes tour, the Asian Film Festival. And then the first quarter of 2020, we're going to have a scavenger hunt. My daughter's a Girl Scout, and that was one of the best Girl Scout events we did, and I decided we can do it too, just because we're all big kids at heart, right? So we're going to have a scavenger hunt in January 2020 for our charter members. The other opportunities charter members have are to meet our special guests. In January, FCC Chairman Ajit Pai accepted our invitation to come speak to TiE, and so we'll have an event for everyone. But for charter members, we'll also have a special time with him, cocktails, dinner. We're working out the details. So those are all different opportunities available at that level. So I hope you will be, people in the room are interested in that. We'd love to have you. Marin is still sitting outside, but she or I, some of the others can help you on that. So with that, we'll get to why we're all here tonight. Dr. Kingsmore and Ms. Benson. We look forward to you and Abe. Thank you for telling us about the title, Unlocking the Potential of Pediatric, I wanted to get it right, Potential of Pediatric Precision Medicine, an area that's new to me and I'm sure many others in here, and we look forward to learning from you. Thank you.
So I wouldn't take too much time. We have the privilege of having Kingsmore and Ms. Wendy Benson here today with us. They both are part of Rady's Institute of Genome Medicine. In full transparency, Wendy was my mentor and supervisor, and she kindly agreed to be here with us today. Just by way of the background, Dr. Kingsmore, who's here, he is the CEO and president of Rady's Institute of Genomic Medicine. He leads a multidisciplinary team of scientists, physicians, and researchers who are guiding precision medical care of critically ill children. As an expert in genomic and system medicine research, he holds the world's record of fastest sequencing in 19.5 hours. As you will hear throughout this presentation, these are very young children who are critically ill. Timing is of essence to find the cure, and what you're looking for is sort of a needle in a haystack. Dr. Kingsmore, he has many honors and degrees, but briefly, not to go into everything in detail here, before he joined Rady's Children, he was at Children's Mercy Kansas City Hospital, where he was founding director of the Center for Pediatric Genomic Medicine. Before that, many years before that, he was a faculty of University of Florida. He got his doctor's medical degree at Queen's University of Belfast. He's a clinical immunologist, and he did his residency at TiE Medical Center. We really appreciate Dr. Kingsmore. Ms. Wendy Benson, she is Vice President of Strategic Initiatives at Rady's Children. She is a clinical and life science industry executive for more than 3 decades, perhaps. Not to time all of that. But she has been at large organizations such as Thermo Fisher, Illumina, Roche, and smaller startup organizations. Again, not to go in super detail, she holds a bachelor's degree from WashU, University of Washington in Seattle in chemistry, math, and statistics. So, overachiever, clearly, and from Taiwan. Let me quickly introduce the subject matter, and then I request both the speakers to come to the table. And I have a very short presentation to kind of introduce the subject matter to you. So we were to think about how this all comes into play, the reproductive journey. There were 131 births worldwide in 2017. It starts with the preconception carrier screening. This is where we would be looking at all the inherited disorders. and then reimplantation genetic testing, where you would take a single cell from the embryo and look for any disorders and chromosomal abnormalities. Then going into prenatal, again, we're monitoring the health of the child, looking at all the genomic disorders that could occur during pregnancy. And once the newborn arrives, then there are tests that hospitals are required to perform. And they're looking, this is the topic of discussion today. You will see that there are about 7,000 rare diseases that are known, and different states require only a handful of them to be tested. So you can imagine how many are left untested. And then of course postnatal. So I'm kind of just walk you through different stages, didn't give you a moment to read through it, but we would be focusing on the newborn screening component here today, where we assess the health of child at birth, and then look for the treatable genetic conditions. As I said, about 7,000 rare diseases. The way the rare disease is defined by NIH is 1 in less than 200,000 people. In Europe, it's slightly different. They look at 1 in 2,000. As a group, they affect nearly 1 in 10, so about 10% of the US individuals. We wouldn't go into all the data. This is taken from Dr. Kingsmore publication. About 18% of the pediatric hospitalizations are associated with rare disorders, and about 35% mortality. So, in this day and age, it's hard to fathom that we still have to go through it, but this is a real issue. And I've mentioned that different states in the US, they have different compliance and guidelines, but now about 34 core conditions and 26 secondary conditions, and I could be wrong, might be changed by now. That's all out of 7,000 with all the other screening for. So with that, the technology that Rady's children is employing is about whole genome sequencing. And with that, I'm going to request both Wendy and Dr. Kingsmore to come to the podium and introduce the subject. And we'll have an opportunity, I hope you won't mind, ask questions along the way.
Super. Nice to be here this evening. Thanks for the invitation. Thanks for the lovely food. I really love Indian food. I grew up in Northern Ireland, and we have a excuse me, a large Indian community and some really excellent Indian food. And one of the things which I struggle with in the US is how difficult it is to get decent Indian food. So I love going back to Ireland or Scotland, where I can get some really good Indian food. Okay, I apologize for being late. My board chair had to get a board packet tonight, and so Wendy and I were working on it until one of the two of us had to leave, and she got the short straw, so she came out here, and I got the long straw, which meant I got to finish the packet up. Okay, I'm going to give you a case example. I'm going to talk a little bit about this subject. I don't have any conflict of interest. Thanks for the introductory slides. So you saw that continuum of opportunities in terms of genetic testing. We're focused on newborns. This bold prediction from Francis Collins says that shortly we will be screening every baby's genome at birth. That's not happening today. where we are focused on is an area where even today it makes economic and clinical utility sense to do so, and that's in children in intensive care units. And so I'm going to talk about Sebastiana and Maverick and Riley. I'm mainly going to talk about Maverick, so I'll just talk briefly about Sebastiana. She's almost 3 years old right now. When she was born, she's had seizures. We decoded her genome in a couple of days. We put her on an appropriate therapy for her seizure condition. She's never had a seizure since, and she is developing really well. This is her with Ernest and Evelyn Rady, who are the benefactors who gave rise to our institute. Maverick, I want to talk about. Riley presented as an infant with infantile Parkinson's disease. So the first time she was seen, she was immobile. She couldn't move her arms or legs. Her fists were clenched. She was hypertonic. And the only thing she could move was her eyes. We were able to diagnose her in less than a week with that ultra-rare condition. And she takes L-DOPA every day and is developmentally normal. So I'm going to talk about rapid precision medicine, which is acute medical management guided by genome information. So hitherto, medicine has been practiced without knowledge of our genome content. And if you have genetic disease, that means that your doctor is not treating the underpinning etiology. And what we're doing is to change that by making genome information part of routine medical care. Some of you probably are very familiar with genomes and others of you aren't. So what is a genome? It's the information content for you, for a human being, and in particular for you as an individual. We're all outbred, we're all unique at a DNA level, and also in terms of our appearance and our attributes. And what codes for that is DNA, deoxyribonucleic acid. And your genome is the blueprint for your life, the instructions for every protein made in your body. It's written in a 4-letter language, A, C, G, and T, so it's not like English, but it is like English in the strings of those letters code for proteins, which then code for your attributes. And the genome is 3.3 billion letters long, which is the equivalent of a book, 425 feet tall, if you were to print it on 8.5 by 11 pages. So you get 2 copies of that per cell, one from your mom, one from your dad. And that's really what comprises us, that's our complexity as human beings. How do we decode a genome? Well, this was invented at Illumina. It's called shotgun sequencing, for obvious reasons. So we take a perfectly good genome and blast it to smithereens, so that we have fragments that are several hundred letters long, and then we actually decode the end fragments on either end, about 100 letters on either end of that 600-letter fragment, and that creates the world's largest jigsaw puzzle, which we then solve, giving us the genome sequence, and then we search through that entire space to find the cause of a child's illness. Let me give you an example. So that's an erythrocyte, or a red blood cell, on the bottom left. That's a normal blood cell. And one of the key proteins in red blood cells is hemoglobin. It's the oxygen-carrying molecule in the red blood cell, or erythrocyte. It's coded for at least the beta chain by this DNA sequence. Well, this is the start of the DNA sequence of that gene. ATG takes 3 letters to code for an amino acid. A string of amino acids codes for a protein. So the top sequence is DNA, and the bottom sequence is the start of the protein sequence. So 3 letters to code for an amino acid. ATG codes for methionine, or M, but it also means start. So it means start making a protein. If we change position 20, which is an adenine, to a thymidine, so just 1 letter change, that changes a glutamic acid to a valine. and that is the commonest mutation in the human genome in terms of its disease burden, because that's sufficient to cause sickle cell disease if you inherit a faulty copy from mum and dad. That's the commonest genetic disease in the world. So that's what we're looking for when we search through a genome, 3.3 billion letters of search space, and we're looking for single variants like that. So we do this at Rady Children's now routinely, and in fact we do it now for 25 children's hospitals around North America. And what we're trying to do is to connect the symptoms in a kid with a genetic disease. So children with diseases of unknown etiology are who we specialize in, and we get samples shipped to us. They arrive every morning from such kids. So these are kids who are suspected that they might have a genetic disease causing their symptomatology. And as you heard, there are at least 7,000 orphan diseases. By my calculation, it's probably closer to about 25,000. There are about 7,000 Mendelian or simple genetic diseases, of which we know the basis today of about 5,500. But then on top of that, there are an awful lot of less well-organized chromosomal variants which also cause disease. When you add them all together, as again introduced in the introduction you heard, they're the leading cause of death in children in North America. Depends where you are in the world. In the developing world, things like sepsis or prematurity would be the leading cause of death. But here in North America, it's genetic diseases. So over the last 4 years, we've focused heavily on building a platform to deliver better outcomes for babies with genetic diseases. I told you to tell you a story, so I'm going to tell you a story. This is Maverick's story. Maverick Coltrane, he was admitted, as you can see here, in 2017 at the age of 8 days old, and he was having seizures, and those seizures were unremitting. His medical history was unrevealing as to why he was having those seizures. So what happens when a baby is admitted to an intensive care unit like Rady Children's Hospital is they have a very rapid workup to see what's triggering the seizures, because that then guides the management. So in his case, we were seeing two things on his brainwave activity, his spike waves, so these are seizures, but then he had background burst suppression, which suggests a particular form of seizure disorder, a genetic cause, which has a very bad outcome. He has a fairly thorough workup there. I'm not going to get into it, but basically we've ruled out a lot of common causes of seizures in the baby. He started on empiric treatment, so treatment based on a protocol for seizures in general, not for any specific cause, but based on treatments that have been used that are typically effective. And by the next day, unfortunately, he's still seizing, and he's now on 5 different drugs. And he's now been intubated because the last of those drugs stopped him from breathing, and so he's on a ventilator to help him breathe. At that point, the pediatric neurologist, Jeffrey Gold, who's in the intensive care unit that week, starts to broach the subject with Maverick's mum and dad that he's likely going to die, and that if he does survive, he's likely to have permanent brain damage. And we do that in cases like this because we want to minimize suffering. If there is no treatment available and the course looks hopeless, we start to move toward comfort care. These are the main causes of neonatal seizures as we understand them today. This is taken from a textbook. It's not right because it's in a textbook. It doesn't reflect the knowledge which isn't made its way to textbooks. But you can see genetic diseases, according to this, are responsible for about 1/10 of infant onset seizures. In fact, it's a higher proportion than that. We never had a way really of picking them up hitherto. And in total, there's more than 1,000 genetic diseases that can cause seizures. Now, why this is upsetting, these are specific genes that can cause seizure disorder. So each of them is responsible for its own disease, a gene attached to a disease. And each of them, as you can see, has a quite different treatment. And this underscores the problem that we have. If you're giving a generic treatment, it's probably the wrong treatment if your child has a genetic disease. By decoding the genome, we find the gene that's responsible, and we're able to do a database lookup and get the appropriate treatment. It's really quite simple and logical, but for a pediatrician, what I just told you makes absolutely no sense. That's not the way physicians are trained. Instead, we're trained to use our clinical acumen and skills to formulate a differential diagnosis, and then to interrogate those things one at a time, and to treat based on the most common and likely cause in a kid. It's not to decode a genome and look for needles and haystacks. So we started this work in 2011 in Kansas City, and in the early studies, we were able to see the natural history of genetic diseases with old-fashioned technologies like microarrays and fluorescence in situ hybridization and single gene sequencing using traditional approaches. And we were diagnosing a genetic disease in about 8% of the babies, and really none of them were receiving precision medicine because those test results typically took 6 weeks to 3 months to come back. We now live in a new world where we offer rapid precision medicine with a genome sequence that we can turn around in as little as a day. And these days, about 1 in 3 children we diagnose with a genetic disease. And about 1 in 3 we rule out genetic diseases, which is also very helpful to the physician. And then the majority of those that we diagnose, we change the management. And in fact, about 20% of the time we have a better outcome. That may not seem a lot, 20%, but that makes it one of the most profound changes in neonatal care ever. So we do that for Maverick, and here's his diagnosis. And this is the stuff that if you can't understand this slide, just feel sorry for a pediatrician, because they don't understand this slide either, and yet this is the stuff of this new world of genomic medicine. So we have the disease, it's called paradoxin-dependent epilepsy. It's incredibly rare. This is the gene name, which is not really helpful to anybody, but that's the place in the genome that's affected. It's recessive, autosomal. That means that mom and dad are carriers. Both contributed a diseased chromosome, and our baby is affected. And then these are the variants, and we have 3 different nomenclatures depending on the genome coordinates, the gene coordinates, and the protein coordinates. And trust me, physicians don't understand any of that. These are both likely pathogenic variants, and that gives us the definitive diagnosis. Okay, this is something that we do learn about in medical school, which is biochemistry. And this is brain biochemistry. And here specifically, we're breaking down lysine, an amino acid, to acetyl-CoA, which is an energy molecule. And this is the protein which is broken, ALDH7A1, in this disease, paradoxin-dependent epilepsy. So this is like a river, and the different proteins, the different enzymes, they trigger going from one step to the next step to the next step. If one of the proteins is broken, it's like a dam in the river, and upstream of the broken place, you have a flood. And so we have way more of this particular thing here than we should have in a baby's brain. It converts to this, and unfortunately this complexes with vitamin B6. So Maverick is dying because his brain has no B6. He actually has plenty of B6, but it's complexed to this other molecule. It's not free to do what B6 needs to do. It's a cofactor in 25 different enzymatic pathways. So the good news is, despite the fact that he has a very rare form of epilepsy, there's a treatment First of all, and again this is common sense, he lacks B6. Let's give him tons of B6. Let's give it to him intravenously. And then on top of that, let's switch off this troublesome pathway by restricting how much lysine we put in his diet. And that overcomes some of this problem. So we start those 3 treatments, and his EEG, his brainwave activity, goes back to normal. He stops seizing, and within 36 hours, he's off all 5 anti-epileptic drugs. He's breathing on his own, and he's breastfeeding. And he goes home fairly soon thereafter. And this is him last February. He's a bit bigger now, and he's healthy and doing great. So, yes?
I just wanted to know, Mary, what age was he when he came to NICU?
When he arrived in the emergency department, he was 8 days old. A typical case. These diseases have an onset at birth, or within the first couple of weeks of life. Now, what I was going to do, if it's possible, we'll just see. I just arrived, so I didn't get a chance to give a heads up. But I have a video of Maverick, and it retells his story through his mum's eyes. So let's see if we can hear that, okay? I'm hoping we can. No, we don't have sound. Is there another? Is it possible to get sound? Yes.
It's not attachment, I wish you. You might have to say.
If we don't, it's okay. I can just keep talking.
We're all in control on this screen.
Oh, is it? Yeah, it should go through the HDMI.
They have
Check
to
over there,
set
like you're on
here, but so, yeah.
Well, it's a really cool story. You can go to our website. It's Rady Genomics, R-A-D-Y, genomics.org. And on that landing page, there's a video clip. And I believe it's Maverick. And it's about 6 minutes long. Okay, I have a couple more slides. Is it okay for me to keep going? Yeah? So I want to sort of zoom out now from a single case to how we hope to change the world. And it starts with a game plan to scale what we do to meet the needs of every child in the US. And so in order to do that, we need to think about, well, who are we helping and how are we helping them? Clearly seizures, that's this group, are very common. So they constitute over 1/3 of the babies we test. And in 44%, we get a diagnosis. It's not quite a half, but that's close. And 81% of those diagnoses, it changes the treatment. So that's a great starting point. Newborns who are having seizures in intensive care units. But look at some of these other things. So there's heart failure. So it's only 10% of our patients, but we make a diagnosis 71% of the time. And 90% of those babies, it changes how we manage their heart failure. Pretty much the same is true with hypotonia. So that's floppy babies. 12%, 63% diagnosis. 90% we change the management. We now have a gene therapy for the commonest cause of floppy babies, commonest genetic cause. And we can now give that, we have to give that treatment in the first couple of days of life for it to be effective. So that's a great example of another indication. Hypoglycemia, so babies with low blood sugar. 10% of the cases, 38% are genetic. And so giving them more sugar ain't gonna help them. You gotta fix the genetic condition. 60% of those have changes in management. So this gives you a nice overview of how seriously ill these children are and the types of interventions that we're making as a result of a genome-based diagnosis. So overwhelmingly when we ask doctors, is this helpful? Once they get the hang of it, they say yes, and the same for parents. By and large, they understand the results and they feel that it was helpful in terms of their child. And there's kind of two stories, there's two sides to that coin. There's the stories like Maverick, where we save his life, and he gets to go home and grow up and be a big boy and be healthy. But then there's the other parents in whom we get an answer, there's no treatment, but they now know what the diagnosis is. The doctor knows what the prognosis is. He can share that with the family, and he can give the family back control over decision making. They decide how much to push in terms of medical management, when to move to comfort care, and what that will look like. They may want to hold their baby, baptize their baby, they might want to take their baby home. They can make plans for how they would like their baby's life to end. And what we found, very surprisingly, is that it's those families who are the most grateful for what we do. They experience the most profound change in terms of what we do for them. Totally surprising. It's not so much the ones in whom we have effective treatments. This is the world's literature to date. So 840 children have been tested worldwide. It's now spread to Australia, Canada, England, as well as the United States. So it's not just us anymore. And overall, we're all finding roughly the same thing, which is 1 in 3 gets a diagnosis, 1 in 4 has a change in treatment, and 1 in 5 has an improved outcome. So I'm just about finished. I'm going to hand over to Wendy, but let's just recap. So the first human genome, $2.7 billion, 13 years. The first medical genome was actually a South Korean called AK1, and it was published in 2009, $2 million, 1.5 years. The first rapid genome we did in Kansas City. It took 2 days. At that time it was revolutionary. Our first world record was also set in Kansas City in 2015, 26 hours. And that was also the year the first of those efficacy studies that I just showed you was published, again by our team. Last year here in San Diego, we set a new Guinness World Record of 19 hours. That's time from a blood sample to calling the doctor with the diagnosis. And it was last year also that we published the first cost effectiveness data and showed that this could potentially save at least $3,000 in hospitalization costs per patient we tested. And there's me with Mr. Guinness, looking very happy. And Mr. Guinness costs $8,500 an hour. That's quite a billing rate, isn't it? So this is where we are at the end of 2019. We're trying to implement this at national scale. We're in 25 children's hospitals. There's a list of them, or 23 of them. And they go from Miami to Boston, all the way out to Honolulu. Wendy's going to talk about Project Baby Bear, so I'm not going to talk about that, but we also have a partnership with Vermont Oxford Network, who are a quality improvement organization for 1,200 NICUs all over the world, and in particular in 30 different countries. So this is kind of our channel whereby we want to do this across North America. And we are adding new hospitals as hard and fast as we can. Right now this is not reimbursed, and so we're heavily dependent on philanthropy and corporate philanthropy to allow us to do what we do. So this is what's ahead of us if we look out into the future. We're developing a new healthcare delivery system. For the last 7 or 8 years, we focused on the middle box, the green box, a fast test to diagnose a baby. But now we're adding in the other parts, realizing that we have an untrained medical workforce and we have institutions who don't realize what I've just shown you, the power and the value of genome sequencing. And so we need an integrated, fairly comprehensive delivery system to enable regular pediatricians throughout North America to do what we did for Maverick. And that's what we're building currently. And as part of that, we're focused on, as quickly as possible, reaching 10,000 children sequenced. This is a goal we set in 2018, at the end of 2018, and we're currently raising funds for that. We anticipate that's going to cost us about $90 million. We've sequenced 1,000 babies' genomes as of July, and so we've got about 9,000 to go. But not only are we doing that, but we're collecting all of that data in a knowledge base. One of the sad things about many of these diseases, and again, in the introduction, you did a really good job of prefacing what I'm saying, many of these diseases don't have treatments. And so this knowledge base, we'll be partnering with pharmaceutical companies to help them, to help guide their development of new drugs for these rare diseases. Many of these diseases, up until now, were not picked up in time to develop a drug, or weren't picked up frequently enough to develop a drug. With this technology spreading across North America, we can realistically expect to pick them up at birth, and also to pick them up in a much larger proportion of children. So I think penultimate slide, rapid precision medicine can be successfully implemented in the care of critically ill kids today. The rapid turnaround time is transformative. It allows medical interventions to happen in the intensive care unit that can save lives and reduce suffering. And in particular, we're very excited about kids with seizures or encephalopathy, if it's of unknown etiology, since they are a great group to focus on initially. This is my team. There's me, and there's Wendy, and this is our teammates. We are dependent, as I said, largely on philanthropy, and so many of the families that fund us are here in San Diego County, like the Liguri family, the Simonicus family, the Rady family, and we're also dependent upon help from NIH and companies like Illumina. And this means to God for creativity, to friends for help. That's the end of my stuff. Do you want to just jump in here, or what do you want to do?
Maybe there's some questions. Are there questions for Dr. Kingsmore?
First of all, it's wonderfully encouraging and heartwarming to hear your success, so congratulations. I have a question for the treatment. Do you ever find that, let's say for autosomal recessive, that you don't have a treatment and perhaps the only treatment will be to edit the gene, or in a multi-gene, polygenic situation, several genes, in order to create an effective outcome?
Yeah, that's a great question. So the diseases that we're focused on exclusively right now are single gene diseases or else chromosomal anomalies. So they all affect one place in the genome. So we're not doing polygenic diseases or common complex diseases. This strategy doesn't yet really work in those more complicated conditions. It works beautifully for these rare inherited diseases. And in these diseases, if you've got the mutation, you get the disease, and if you've got the disease, you have the mutation. So it's black and white, not like common complex diseases. So yes, many of them don't have effective treatments. And so thinking through how we're going to develop treatments is an important part of our future thinking. and a driver behind us partnering with pharmaceutical companies. And we are entering an era now of either gene therapies or gene editing or antisense oligonucleotide therapies. And some of those are being developed for very, very rare diseases, and sometimes even for single variants. And so right now, today, I can't say that we are going all that way, but our future plan is really to get into that. We think we'll have enabling knowledge to capitalize that, but that's somewhat predicated on being able to scale up the volume.
I have a good question.
Sure.
Kingsmore. In terms of the getting to the results quickly, how important do you think data analytics or bioinformatics?
Could you repeat the question?
Sure, be happy to. Question was, for a rapid result, how important is the bioinformatics, the analytics side of things? And everything's important, so that's what we've learned. Initially, the bottleneck was the sequencers were very slow and used to take lots of runs to get a genome. The sequencers now are exceptionally fast. It takes 16 hours to decode 5 genomes using the Illumina NovaSeq platform. The informatic piece has also gotten much faster. Back when we started this, we used to have to use a supercomputer, and it would take 12 or 24 hours to process the genome. That's not possible in 10 or 15 minutes using a Dragon system. This was a company from La Jolla called Genome, who were purchased last year by Illumina. So that piece also is fairly well solved. The interpretation piece is still a bit clunky. We use informatic tools, and there are a number of companies who develop those. There's still a bit of a way to go. We started to use artificial intelligence. What we showed in a paper this March or April was that we can use AI to diagnose a genetic disease in 5 minutes or less than 5 minutes by automated interpretation. That's not something yet you can do on a real live human being because of the regulatory landscape, but in practice it worked pretty well. But there's other bits like how long does it take to get a blood sample? How long does it take to get parents to agree to a genome? How long does it take for a doctor to think about ordering a genome? And then how long does it take after return of results to actually start the effective treatment? And those are the bottlenecks that really are the scary ones. We can crunch down the time of decoding a genome, but some of those other bits are somewhat outside our control. We're very aware that we're not very effective at coordinating those. That's why we're focusing on this healthcare delivery system rather than on a test going forward. Yes, sir.
Probably is the question is more like understanding the part that you said you are focusing in answer to that question on the genes that are only one letter changed.
Yes.
The one that you said is more complex is multiple, yeah? So explain that why that one is still not have a systematic approach for it.
Yes, so there's 2 types of genetic contribution to disease. There's simple genetic diseases. This was that monk called Gregor Mendel who bred peas and discovered some of the critical laws. And there, a variant in a gene is necessary and sufficient to cause the disease. And they are very common in newborns, 16% incidence in an intensive care unit, the leading cause of death, and one of the leading causes of admissions in children's hospital. Most of us, we've survived our genome. Most of us don't have a bad genetic single gene disease. We now are into what we call polygenic stuff. And in that, many genetic factors come together to affect your risk of developing that disease. Rheumatoid arthritis is an example. Heart disease is another example. Alzheimer's is another example. But it's also about environment. Do you smoke? Are you overweight? Things like that. It's really difficult for us to provide precision medicine today for complex diseases. because we don't know the math. All we can tell a patient is you're at let's say, a 4-fold increase of developing prostate cancer.
What could be the, sorry, I think my voice is loud enough, but what could be kind of a systematic research if you want to suggest something for this kind of the last group that could be a systematic, let's say for heart diseases, monitoring something and continuously measure the risk factor increasing over the time and make an intervention?
Well, we have a thing that we call polygenic risk scores, so it's kind of the state of the art. And so this uses the same technology that you do for genealogy. You see these guys on the adverts every night in Life. You know, I thought I was German and I used to wear leather pants, and then I discovered I was actually Irish. All right, good for you. So it's the same technology, it's microarrays, and we measure about 500,000 points, what we call single nucleotide polymorphisms, so points in the genome, and hundreds, thousands of studies have been done so that we understand what they do for your risk overall for well over 100 different diseases. And you can order that. Companies like 23andMe offer some of that. There's a thing called All of Us, which is going to enroll 1 million US citizens and offer them that, as well as looking at their medical records. As I said, the utility of that in changing outcomes is not well proven. We really don't have data based on populations that shows that will impact, longevity or health in an average population. A lot of it has to do with, well, did you think your risk was high enough that you actually stopped smoking? Because if you didn't make that lifestyle change, knowing your genetic risk didn't help you in it. It's an area that's going to take a long time to reduce to practice, and it's already cost tens or hundreds of billions of dollars. Instead, we focus on something where we can make a dramatic impact on suffering and mortality right now today in 2019.
Thank you. Thank you.
I think I've exhausted the questions. So that means it's Wendy's turn. Do you have one more question? Yes.
When will we get to a point where, is Europe well mapped and understood, and Asia, and from India, I want to know about that billion. When will we have a view of, I see no point today going to find out my, connections, if you will. Because the rest of the population where I come from hasn't been mapped yet?
Yeah, actually, you might be surprised. It's not yet available in a test that you can spit in a cup and send it off. But there is an ethnicity project out of Singapore. The guy who's in charge of it is called Stefan Schuster. And he's been sampling ethnic subpopulations across Asia, literally thousands of them. So he goes to isolated communities, whether it's in India or in the Himalayas or in Southeast Asia or northern Russia. So there's thousands of these ethnically homogeneous subpopulations, and he decodes their genome. And he's put that into a master database. And so that data now does actually exist, and he can take individuals and he can tell you your ethnic derivation with great precision. He doesn't do that commercially, but I just heard him talk. He was here in San Diego last week or the week before, 2 weeks ago. And so I got a progress update on it, and it's actually really exciting.
Thank you.
I have one question.
Sure.
Rady is doing all this pioneering work. Are there other hospitals like you doing similar pioneering work? Because you've shown from Rady knowledge you're gaining, you're transferring to different hospitals in your network. But are there similar hospitals like Rady in the US or abroad doing such work, and how are you sharing that information?
Yes, I did show you kind of a picture of the world's literature. There are at least 10 different groups doing parallel work. We're a little bit unique because with the Browning Research Institute that we designed around this, which means we're very integrated into the hospital. Traditionally, research institutes are set up separately from a hospital, and that means it's quite difficult for them to get into the implementation phase. But there are other groups who are trying to do what we're doing, and some of them on a bigger scale, much bigger scale than what we're doing. So in particular, we can think about Genome England, where it's now national policy to decode genomes of inpatient children. That doesn't mean they're doing it today, it means it's policy and they're figuring out a game plan to implement that. Same is true in most of Australia. And then there are places like Texas Children's, in Houston. There are a number of places that have similar programs to us. We are a little bit unique also because of the gift that Ernest and Evelyn Rady gave us. That gives us a unique resource to be able to do some things that other people might not be able to dream about.
Thank you very much. Thanks, Ave. Thanks, Stephen. I'm going to give you guys a real quick update on a pilot project we're doing across the state of California. We're calling it Project Baby Bear. And the reason why this is important, Stephen told you, we're a very small research institute. There's less than 60 employees. And we're trying to figure out a way to make this sustainable. So as you guys know, as a bunch of entrepreneurs, we've got a couple different ways to do that. One's to try to get it reimbursed. And in order to do that, we need to demonstrate clinical utility and also comparative effectiveness. So specifically, what would happen to these kiddos if they did not have a wrappable genome? So we were able to get a pilot project done across the state of California, and I thought I'd give you a quick update on the results. We're 1 year into this pilot, and I brought a couple copies of our second state deliverable. So every 6 months or so, we provide an update to the state of California on how we're doing. And I'll just give you a quick overview of the program. So Baby Bear, awesome name. So for those who don't know, the bear is a California state animal. Gave us a $2 million grant about a year ago, and we are working with 5 hospitals across the state. So UC Davis Children's Hospital in Sacramento, Benioff, Oakland, Valley Children's, which is in that Central Valley, kind of Fresno, Madera area, Chalk Children's in Orange County, and of course, Rady Children's here in San Diego. And we did this for 3 phases. So phase 1 was teaching them how to do this. So we have nice diversity across these hospitals. Not all of these hospitals are associated with academic medical centers, and not all these hospitals have a lot of genetics available for inpatient testing. So we thought this was a great cohort to figure out how this was going to scale to every kiddo that might need it. So we spent time as very similar to the 3 pillars we talked about tonight for TiE. So obviously this is addressing a funding pillar, but also a massive education pillar and a networking pillar. So we have this great cohort of sites that we're working with. Phase 2 is where we're spending 80% of the money, and this is doing what Stephen outlined. So this is trying to figure out which inpatients are likely to benefit from a rapid genome, and then not only returning a test result, but helping that clinician figure out what this means for the
clinical care of that patient. And then phase 3 is all the health economics and trying to model this. So inclusion criteria is pretty broad, but they need to be a Medi-Cal beneficiary. So this is done by the state of California, not by private insurers. And we want to get them really quick. So if you've exhausted every other diagnostic modality that you can do, then chances are that we're not going to be able to impact the care of that patient. So we want these really quick. So if your little spidey sense goes off as a neonatologist and you're not exactly sure what's going on with that patient, my motto is, when in doubt, send it out. And then there's specific exclusion criteria. These are kiddos that we know probably wouldn't benefit, and that's like they already have a diagnosis, it's isolated prematurity, and a whole bunch of other words that I cannot enunciate. What we're looking for endpoints, this is not a research project, this is a quality improvement project. So our biggest endpoint is improved outcomes, comparative effectiveness, and then how do the physicians feel about what would have happened in the absence of the care. So as of the end of September, we've done 116 cases. Our average turnaround time is 3 days. Now, standard of care is about 6 weeks if you were to send something out to get these results. So 3 days has been pretty phenomenal. 92 of these cases we reviewed for a change in management. So that is, did something happen because of this result? And 39% of the time, something did happen because of this result. We've got some great case stories. Stephen talked about some of the positive findings, like a diagnosis for Maverick. We've had a negative finding that was really informative. We've actually had several of those in Baby Bear that were kind of surprising. We also had a kiddo that Child Protective Services took away from their parents because they presented to the emergency department with multiple breaks and fractures. And of course, the clinician suspected probably some abuse at home. And then we found a very rare genetic condition that described what that kiddo was going through, and the patient was actually returned to his family. So not things exactly that we expected to see, but it's been a great project for us. So 43% of these tests have resulted in a diagnosis, 39% change of management, substantial savings from getting babies home sooner. So far, our interim results have shown 225 fewer days in the hospital, massive procedures, and these procedures suck if you're an adult. Can you imagine if you're like 3 days old and getting a muscle biopsy? These are not things you want to do to these kids. 12 fewer invasive therapeutic procedure, again, horrible things to do to a baby. And we know already that we've saved somewhere between $1.4 and $2.4 million. So we had a subcommittee hearing in San Diego last week with some key legislators. The chair of the Innovation for Biotech Committee was here, Kevin Mullen out of Sacramento. Pro Temp Senator Tony Atkins was here. Todd Gloria was here. Marie Waldron was here. I hope I didn't forget anybody. But we gave them a verbal report of how we're doing. It sounds like they read the state report, which was actually written not for scientists, but actually for legislators. And we're looking forward to going around and working with our partner hospitals and communicating those results as well. So this is really super interesting. These are the zip codes of every kiddo so far that's been part of Project Baby Bear. You can tell they go all the way down to the border and all the way up to, what is that, Reading? And also pretty far out to the east as well. So even though our 5 hospitals seem to be kind of central to Southern California, I'm super happy that we're getting some results in Northern California. So next steps on this are obviously to try to make it a permanent covered benefit across the state of California. We're also working with private insurers and having conversations with them about the evidence that this is generating. So please make sure you go home and tell at least 5 friends what we're doing with Project Baby Bear so we can also increase the awareness. So we think this is also something that we can do at more states across the US, but it doesn't suck that California is the first one. So Florida now is doing something to sequence 50 critically ill children with one of our partner hospitals there in Miami, Nicholas Children's. Michigan, I love these guys. They don't have any money yet, but they're already calling it Project Baby Deer, which is awesome.
We're also in conversations, thanks to Stephen and his travels in North Carolina, South Dakota, Utah. Do you guys know that the state animal in Utah is a bee? Because they're busy bees? So they're thinking about calling it Project Baby Bee, but we might need some marketing help on that one. Okay, and Blue Shield now is covering this for the state of California. It's going to take a while to implement this, insurance contracts, and then there's a couple federal bills out, which we're also super excited about. One was sponsored by our local congressman here in San Diego, Scott Peters, and his Republican counterpart, John Shimkus from Illinois. And this is HR 4144. It's called Ending the Diagnostic Medical Act. And if it gets funded, it's 3 years of paying, helping Medi-Cal or Medicaid across the U.S. get reimbursed for doing this testing for these kiddos. So with that, this is the Baby Bear team. And we'll take any questions. Thanks for your attention. It's nice to see all of you again.
Good question, Rady.
Yes.
Mike. No.
Oh, sorry. Sorry about that.
Many of these children, they happen to come from...
By Mike. Mike's not on. You're soft-spoken. Yeah.
Many of these children, they happen to come from poor families or families with limited resources. How are you and the society handling those cases? They do not always have the resources. $3,000 or $3,500 for many in this audience may not be much, but for those poor families, especially for the sick child.
So that's what's so awesome about Project Baby Bear is it's covered by the state of California, so parents aren't seeing any bills for this. And I think that's true across most of our partner hospitals. They're not passing any of this cost on to those kiddos or parents, whether it's private or public insurers, which is awesome.
What about pharmaceutical companies? Are they helping out in terms of developing new medicines or something along those lines?
So Stephen kind of talked about this a little bit. So we're super interested in partnering with pharma. We think we have found things that we did not expect to find so far. And so we're just starting now to communicate that and figure out what this might mean for developing new therapies or maybe repurposing some drugs that they may have already developed. The pediatric use case is different than the adult use case, but we're really hoping to do something about the conditions that we could treat that we don't have treatments for today. Stephen, if you want to add anything out here, feel free to help out.
So I hear 1,000 babies' genomes being sequenced and stored somewhere, and I have to tell you that kind of scares me a little bit about what could happen to data over their lifetimes. What do you all do about that to address data privacy concerns?
Definitely help me out on that one, Steve.
He's the smart one.
No, but I do know the answer to that. So first of all, in California, the data is treated as part of your medical record, so it's owned by the families along with their medical record. The data currently sits in the same environment as the medical record, so that's behind Rady Children's Hospital firewall, alongside the rest of the medical record. In North America, we're very fortunate. In the US, we're very fortunate that we have a good, strong genetic anti-discrimination law called GINA, the Genetic Anti-Discrimination Act. It doesn't cover all things, so it won't prevent you from being refused for life insurance. And if you're a parent in the armed services, you're exempted from GINA. So as politicians often do, they exempt themselves from their legislation and other government employees. And so we have to caution parents about that if we find something in their genome, because we often test mom, dad, and baby. And they're in the services. They have to think that through the risk of it affecting their employment as a member of the armed forces. So those are a couple of the things. But living in a children's hospital, I am very, very aware of the relentless attacks against our infrastructure every single day. From every bad place on earth, there are people trying to cross our firewall, and that's probably true of many of you in business. It's relentless, and we have a dedicated team to protect our data's security. And genome information is not really any different ultimately than every other piece of information in the medical record. Does that answer your question?
That does. And what about the sharing with pharma piece? And I understand you're a long way off from being commercially profitable and all that, but ultimately you are using a handful of children's genomes to benefit financially a pharmaceutical company. So what do you do about that?
Yeah, I think that's a really important question, and that speaks to oversight. So we now have a parental advisory board. It's brand new, and if any of you want to join it, let me know, because we're still small. But that's one important oversight mechanism, is to make sure that the public in San Diego are giving us their opinion on what we're doing. We have a lot of other sort of fiduciary oversight mechanisms. We have a scientific advisory board about our science. We have a board of directors about our financials and our strategic direction. And every research document and every research protocol, of course, has to go through two completely different tracks of regulatory oversight. One's called the Investigational Review Board, and that's run out of UCSD, so that's a committee who evaluate the risks and the benefits of every research protocol. And in those documents, you have to speak very specifically as to some of the issues that you're asking about. So there's that. And then on top of that, there's a hospital regulatory and compliance body who are separate and cover everything that we do on top of the two interconnect. This is California, so we have more red tape. I've now practiced in a lot of places in the US, and I have to tell you, California has more red tape than probably 4 or 5 different states combined. So we are also overseen by the Clinical Laboratory Improvements Act. That's federally mandated by the College of American Pathologists and by the state of California. So regulatory compliance is a big chunk of what we do, and it's very important to be safe. The downside is it does contribute a ton of cost to what we do. You can now decode a human genome for less than $1,000, and it costs us almost 10 times that to do a clinically regulated genome in a critically ill baby.
Thank you.
A long answer to a short question.
I will just say from a data privacy perspective, it's actually good that you're doing this and innovating in California, because that makes me more comfortable that all these regulatory agencies are out there and you're working with them.
It seems very intuitive to me that this project would be financially beneficial to the system, but someone has to make this decision. As a practical matter, what is the threshold of savings that you have to hit, do you think, in order to get reimbursement? For example, if you demonstrate that it provides $1 of savings, is that enough to get you across the finish line, or are there so many things like that that you have to get like a 200% savings in order to get over the finish line?
Yeah, that's a great question. I've gotten a couple different answers on it, so I'll tell you what most folks have told us is the most important thing that is to focus on is the improved outcomes, and the financials will follow. So something to think about relative to the math for these patients. So what we've seen so far is the impact on the healthcare system with that kiddo as an inpatient. But if you go to Maverick's case, where he stopped seizing, went home, doesn't have any, tubes and additional therapies, the cost of not having a neurologically devastated kiddo across his 18 years is enough to probably cover the cost of sequencing every kid that needs it in the state of California. So I think you're right. I think people are intuitively understanding that, and we've taken a really conservative approach to how we're doing the math. So I think everyone's kind of connected the dots on that.
What else can be done to further lower the cost of this genome sequencing?
So let me make sure I understood that. What else can be done to help lower the cost of this genomic sequencing? That's a great question. Thank you for that. We would love to get more volume into San Diego. So we have a huge sunk cost in developing infrastructure to do this rapidly. Think about most reference labs out there that do testing. They wait for 3 to 5 to 7 days until they have enough samples queued up to make sure they're using all their equipment in the most efficient manner possible. We can't do that. We have a sick kiddo, we're going to put on the instrument right away. So if we had more samples coming in every day, then we could leverage that cost, and that would help bring the cost down a lot. And then we need to figure out how to automate some of the things that we have people doing today, and so we can repurpose those people to do other things we need them to do. Did I miss anything, Stephen?
You could work with those legislators that came, Senator Atkins and Assemblyman Gloria, with efficiencies, right?
Yes. Yeah, they've been great thought partners, and we have a new Secretary of Health under the new Gavin Newsom regime, who is a pediatrician. So we're super excited about having him there, and we've already started having conversations with him. So we have a very strong government affairs group at Rady Children's, which has been really well connected in Sacramento. Avi, you're getting your steps in tonight.
Well, thank you for giving us an enlightening chat. I would think that all the discoveries you are making at for the children's, some of them maybe could be applied to the adult population. Is there any effort to maybe transfer some of these methodologies or protocols or discoveries to the adult populations and maybe monetize it so you can do some other things? You mentioned that you could do some more work or more requests to do these things. Would it be too much out of the way to maybe get the adult population to contribute to that?
Great question. I could use some scientific help here, boss.
Yes, so we did do a pilot project with Mass General last year looking at adults with acute myocardial infarction. It's a project called One Brave Idea, and we decoded the genomes of 50 adults. So they have that pilot data, preparing it for publication. But that's very much the same idea. So again, it's a medical emergency. You need the data immediately. And the open question, which I'm not sure they could answer yet, is would it be cost effective to add a genome to the list of things that you do when you have a heart attack?
Hi, yes, I love the data. It's great to see that. And for those who don't know, my daughter was sequenced at the age of 15. I think one of the things that would be interesting to see is because you have all of her data, is to see how much was spent on her up to the age of 15, and then throw that into your numbers too and say, if Lily Grossman had been sequenced at the age of 1, here's how much would have been saved. Here's the emotional capital that would not have spent by her parents and family. But I love the data. It's great. Thank you.
Yeah, it's a great idea. 15 years. Yeah.
Just a quick question. I mean, is there like a Genomics England equivalent initiative that will happen in the U.S. as well? Kind of continuation of a question too. We were looking at NICU, PICU patients, and then there is all of us, which includes healthy population as well. But is there going to be an effort to recruit patients that could be susceptible or diagnosed with rare diseases or undiagnosed who are ongoing on an Odyssey? So do you think that the U.S. might be looking into a program like that in the future?
Yes, I think this federal bill is a step in that direction. So it's kind of a 3-year pilot program that's been, pitched forward by Congressman Peters and Shimkus. Based on how that plays out, then it could become a covered benefit, but it is called Ending the Diagnostic Odyssey Act. I think the Grossman case of 15 years is a long case. I think the average time for a Diagnostic Odyssey patient is about 7 years, and I think it's 9 different doctors, and I'm sure you and Gay have 45 doctors to find a diagnosis for Lily. So if we can find them as newborns, then ergo you prevent the Diagnostic Odyssey from even happening in the first place. So I don't know if that answers your question, Shika.
It does. I think, and my mind was going more towards pharma collaborations eventually, because ultimately we want to be able to provide therapies to patients diagnosed with rare diseases. And another question that I was going to ask earlier was, how are we thinking about patient incentivization early on so that there is motivation alongside we're doing genomic education via hospitals and practitioners, but also in the general population. So not everyone thinks about 23andMe and Ancestry, but they really think about genomics as, saving lives. There's incentivization built in for patients to be able to share their data, and data to a level where pharma companies can actually use it successfully.
Yeah, you guys all know Luna DNA, the local San Diego company that's trying to do that. So I think a lot of folks are trying to figure out how to make that happen. Do you want to add anything, Stephen? Okay. Thank you guys very much.